I'd like to introduce the second lecture by Dima Sinapova on the tree property. Dima?
Okay, so today I'm going to tell you guys about this theorem, recent result I mentioned yesterday, which is that starting from omega many supercompact cardinals and a weakly compact above it, one can consistently get the tree property at the first and second successor of a singular strong limit. I'll suppose there are omega many supercompact cardinals and a weakly compact above them. Then we can get the tree property at kappa plus, kappa double plus, for where kappa is a singular strong limit. And as I mentioned at the end of yesterday's lecture, the two key ingredients of the forcing construction is interleaving the diagonal supercompact prickly forcing into the Mitchell poset for the tree property. So key so let me say combine Mitchell forcing with the diagonal supercompact prickly from its ice results with diagonal supercompact prickly. So let me start by just mentioning some motivational, past results which have combined in different forms Mitchell's forcing with prickly type forcing. So some relevant past results which I haven't already mentioned. Was there a question? Okay, so the first one is due to Cummings and Foreman. So in the same paper that they showed that the tree property at all of the alphans for n greater than 1 is consistent, they also showed that from omega many one can get from a supercompact the tree property at the second successor of a singular strong limit. So TP at kappa double plus, where kappa is singular strong limit, and they use so a Mitchell type poset, and within the Mitchell poset they use prickly forcing to singularize kappa. Now, so a quick note, in their model the tree property at kappa plus doesn't hold. Actually, one can show that in their model weak square at kappa holds. But then replacing a more standard prickly with the Gittig-Sharon style diagonal supercompact prickly can yield the following result. So this is due by Spencer Unger. I think it was published in 2013, but the result itself was a couple of years before that. That one can get the tree property at the double successor of a singular strong limit kappa, together with failure of weak square at kappa. So again, kappa here, singular strong limit. And in order to even hope to get the tree property, one better get failure of weak square. Okay, so both of these used Mitchell style with this with more normal Pricry and Spencer's result with Gittig-Sharon Pricry forcing. Now, if instead of the Gittig-Sharon Pricry forcing one puts in Itai's diagonal Pricry, then, as I'll tell you today, we can show that the tree property is obtained at both first and second successor. So, okay. So now, let me do, before I start talking about my forcing construction, let me do just a brief warm-up to remind you guys about the Mitchell poset. Just, classical Mitchell poset to get the tree property at omega 2. What happens there? So the picture is the following. We have our weakly compact cardinal lambda. Let's say this is omega 1, say this is omega. So note by that result by Specker that I mentioned yesterday, CH implies that the tree property would fail at omega 2. So one of the things that has to be done in order to hope to get the tree property is to violate CH. So for example, one of the things that needs to be done is to add add lambda many reals. So the Mitchell poset, let me first tell you what it does before I write down the definition briefly. It adds, so it makes 2 to the omega equal lambda, and also makes lambda equal L of 2 while preserving omega 1. So preserves omega 1. So the idea is to blow up the power set of omega while simultaneously collapse all those cardinals here to omega 1. Okay. And the forcing is has two components. Okay. A, R, where A is, well, in the Cohen poset, add omega lambda, so this is denotes the poset to add lambda many subsets of omega. Now what about R? Well, R has, so it's a partial function, it has domain a subset of lambda. So size less than or equal to omega. And for each, let me write it like that, for each alpha in the domain of R, we have that R of alpha is a name for a condition in the poset to add one Cohen subset of omega 1, as understood by this poset at, let me call this A restricted to alpha. Okay. So if one takes a generic for this, if you restrict yourself to any of the alphas between lambda and omega 1, this will induce a generic for this poset iteration, so followed by this, which will collapse alpha to omega 1. So lambda will become the successor of omega 1. Now, how do we know that omega 1 is preserved? And after that, how do we know that the tree property holds? Well, I haven't given you the order yet. Let me give you the order. So A prime, R prime is less than or equal to AR if, well, the first coordinate is what, the only thing it could be, so A prime extends A in the add poset, and we have that the domain of R is a subset of domain of R prime. And for every alpha in domain of R, A prime forces that R prime of alpha is stronger than extends R of alpha. So it's kind of like this, interesting way in which the two coordinates interact with each other. So this poset in itself, has terrible closure, but a key fact in Mitchell's proof is that one can define a closed poset which projects, a product poset which projects to the Mitchell one as follows. So note that let M star be so similar to this with same underlying set, but changing the order as follows. So the order for M star is A prime R prime is stronger than M star AR if, so this is the same, but here in the third item, instead of A prime, we take 1. Okay. So this removes the interaction between the two coordinates. So if A prime less than or equal to A, and for every alpha in the domain of R, which is a subset of domain of R prime, it's forced by the anti-condition that R prime of alpha is stronger than R of alpha. Okay. So by removing this interaction, this poset M star now can be presented as, I'll just write it and then I'll pull the board up. M star is just add omega lambda times, so product, something I'll call Q, which now this is countably closed. And moreover, it turns out that M star projects to M. So this is a key point in Mitchell's construction which makes everything work.
What do you mean that two by project?
I mean that a generic for M star induces a generic for M. Or I mean, you can define an actual projection. So actually, the projection is witnessed by the identity. So if you take the identity, then you have it's order preserving, because certainly if, what's the difference is the order for M star is slightly stronger, that 1 has to force. So it's order preserving, and by playing around with the names, you can show that it's a projection in like the usual. Okay, so any questions about this before I put in the prickly in it? Okay, so now that we have like this, just the basic building block, the Mitchell's poset, well, let me tell you what the forcing poset in our case will be.
Excuse me? So the Mitchell forcing, what does that do for you? Does that give you the tree property, or?
Yes, so this gives you this makes lambda equal L of 2 and gives you the tree property at L of 2. And the way this happens is using the fact that you started with a weakly compact lambda, and that a certain quotient is very nice, which I'm going to talk more about quotients in a little bit. Okay, so now what is our picture? Well, let me write the several relevant conditions. So we have, so the assumptions of the theorem is we start with omega many supercompact cardinals. So let kappa denote kappa 0. And then I have kappa n I'm gonna call their supremum kappa omega. Then let mu be the successor of the supremum, and let lambda be the weakly compact cardinal above it. So kappa will play the role of omega here, mu will play the role of omega 1 here, and lambda will play the role with lambda. So, and here in V, where each kappa n, we arrange it to be indestructibly supercompact, not just supercompact. Okay, so as before defining the poset, let me write down what the tasks of this poset are. So what we want to do, okay, so I'm going to define a forcing R, which R will do the following thing. So make, as before, so remember, kappa plays the role of what omega was there. So we want to make 2 to the kappa equal lambda. Now we also want to make lambda equal mu plus and preserve mu plus. I mean, preserve mu, I should say. So collapse everything between mu and lambda, just like the...
You don't have a kappa.
Hmm?
You don't have a kappa.
Yeah, kappa, I called kappa 0 kappa.
Sorry.
Yeah. Preserve mu. So this is what the Mitchell part will do. Now, what will the Prickry part do? So the Prickry part, just as the Prickry part has to singularize every cardinal between kappa and kappa omega to have cofinality omega, and thereby making kappa strong limit of cof omega, and make mu be the successor of kappa. So this is what the Prickry part has to do. So this is done by the Mitchell's part, and by the Prickry part has to make cof kappa equal to omega and mu equal to kappa plus. Okay, and then, very roughly speaking, how do we get, so we get the tree property at lambda, which will be the double successor of kappa, using so morally the Mitchell component of the forcing will be responsible for that, and we want to get the tree property at mu, which is the first successor of kappa, using using the Prickry part plus certain branch preservation arguments. Okay, so if I was giving a slight talk overview of the proof, this will be it. And the key points. Okay, and now let me actually define what this forcing is, now that we know what it has to do. Okay, definition. Okay, R, well, so it will have three components, One will be the Prickry, and one will be the Cohen component to add a subset of kappa, and one will be a parallel of this R here. Okay. So conditions are of the form A P dot, I have to say, R, where, so A is easy. A is in add kappa lambda, which let me call this poset just A. Now, using the fact that that kappa is indestructibly supercompact, now that after forcing with add kappa lambda, kappa remains supercompact. So one has, so we fix normal measures there. We can fix normal measures there with respect to which to define the prickly forcing. In other words, so this is, okay. One sub A will force that P dot is an element in, let me call the prickly poset I, where, actually I'm going to write this here. So, where I is the diagonal prickly used as in its ice result, which is what I talked about at the end of last time. So this is diagonal prickly forcing. Just to recall briefly, this was the forcing using normal measures un for n less than omega on the p kappa kappa n's, and add the generic sequence xn n less than omega, each xn in here, which singularizes the whole interval. All right, then now what about R? Well, the domain of R, just like here, subset of lambda. Well, what's the support? Recall, mu plays the part of omega 1. So the support here is less than mu. And every R alpha will be responsible for, having partial information about how to collapse alpha to mu. For every alpha in the domain of R, we have that R alpha is a name that's forced to be in adding one Cohen poset of mu, but now name according to whom. So here the name was just, because we only have one first component, just taking add restricted to alpha. Well, here we have to take add star the prickly restricted to alpha. This will, so the empty condition of that poset will force that R of alpha is in add mu1. So what does this restriction mean?
Are they both restricted to alpha or just I?
Yeah. So what does this restriction?
If you restrict F to alpha, you're supposed to change it somehow.
Yes, so that's what I'm going to say next. So what do I mean by this restriction? Well, and this is a known. So it takes an argument to see this, and it first appeared in the Cummings-Forman paper, and I believe also in Unger's paper. It's outlined in one form or another. So one can show, so this is, let me do a lemma. For many, and by many malo, and by many I mean with respect to, say, the weakly compact filter on lambda. For many malo alphas less than lambda, one can show that if the name which of the normal measure, so this name, suppose those UNs are odd names for the normal measures, that this, when you restrict them to the measure one sets of the model by add kappa alpha, projects, the prickly forcing will project. The A names for the normal measures will project to A restricted to alpha names for those normal measures. To be more precise, if you fix, so what do I mean by that? I mean that if you have at kappa alpha and above it you had at kappa lambda, so you can define normal measures in the extension by at kappa lambda, and also normal measures in the extension by at kappa alpha, such that the precree with respect to those measures, the one upstairs will project to the one downstairs. And this follows by characterization of genericity due to Matthias of precree forcings that something is a generic sequence if and only if it meets every measure one set on a tail end. So if you meet all the measure one sets of the extension by at kappa lambda, you will meet all the measure one sets in an intermediate model. That's how one can show that I will project to I restricted to at kappa alpha. And it's actually more technical and more involved than that, but this is all I want to say here. And it's written in detail, I think, for example, in the Cummings-Forman paper. That's where it appears first. Okay, James is smirking. Okay. Does that answer the question? Okay. All right, and then what we want. Okay, so now the interesting part, the order. So this is the definition of the pulse. The three components, at, precree, and what I call term forcing are. Okay, so the way since the orders are So orders, and I'll be defining several orders similar to the Mitchell case. So A prime P dot prime R prime is less than or equals of R A P dot R if A prime P prime is less than or equal AP with respect to at star precree, at star R. 2, domain of R prime extends domain of R. And 3, if for every alpha in the domain of R, well, we have that this interesting restriction A prime P dot prime up to alpha will force that R prime of alpha is stronger than R of alpha.
You can restrict those alphas to be in the good set?
Yes. Yes, for minimal, let's always work with those cardinals. And technically, that restriction is defined often enough, but if you think in terms of Boolean algebras, it's defined always. So let's just, okay. So, I mean, this is very Mitchell-esque, right? Okay. So, all right, so this is one order. Well, now, let me define you what about, we can change the third condition, just like it was changed in the case of M star. Well, instead of restricted to alpha, we can just take the empty condition. So let me define another order with the same underlying set, less than or equal R sub star, where 1 and 2 are the same. So 1 and 2 are the same. The only difference is that in 3 we have that, you know, 1 forces, well, in the right poset. So A star I restricted to alpha forces that R prime alpha is stronger than R of alpha. Okay. So what do we have now? Just as in the Mitchell case, R star projects to R. R star can be represented as a product forcing where one component is at star precre and the other component is a closed forcing, because once in item 3 you require that the empty condition forces R prime of alpha extends R of alpha, you remove the relationship, the interaction between the coordinates. So then you can view the last component of the conditions as standing on its own. And that is closed because those R of alphas are in the poset add mu1. Okay. So some properties. And this has all been it's straightforward what I'm going to write now, and it has been known. It follows from arguments both in James and Matt's paper or in Spencer's papers. We have that R star can be written as at followed by precre, and then times a forcing which I'll call Q. So Q has the underlying set R and the order given in item 3. Okay? And this forcing is mu closed. Okay. Again, one can show that R star projects to R. What about also R projects to at star precre? So, and one can show, and this is, it actually follows from Spencer's results that, so this was already, that the tree property, okay, so if in a little bit, I'll actually denote generics, G's and the like. But for now, let me say in V extension by R, lambda becomes kappa double plus and mu plus. So kappa is singularized. This is due to the precre part. Everything between kappa omega is collapsed to kappa. And this is my picture. So mu does become the successor of kappa, lambda becomes the successor of mu because all of these guys are collapsed by the R. And we do know that the tree property holds at lambda. Okay, so this was in one form or another kind of known.
Also that kappa is a strong limit.
Yes, kappa is strong limit. Okay. What else from the basic properties do I want to say? Oh, and then there's one observation. I mean, I guess it's also due to Spencer, that using Tsai's theorem, one can show that in the R star, the tree property holds at mu, so which is destined to become the successor, which is the successor of kappa. So, but this is in the outer model, V R star. longer. And okay, so we have this. So I mean, just looking at those items, one can say, okay, well, all we need is some sort of a branch preservation lemma to get, so if there is a tree in VR, there is a branch by its arguments in this outer model R star. Let's analyze the quotient, and there are plenty of branch preservation lemmas at our fingertips. I mean, one can do the Magidor-Cholat type of splitting or Silver type of splitting, etc. The one problem, the main obstacle for getting it, the tree property at mu in VR, has been that the quotient R star mod R is the opposite of nice. So one problem. So the main problem really has been in all my time of working on this problem is that the quotient R star mod R is, really not nice, not amenable to any of those branch preservation type lemmas. Yeah. Because usually for those preservation type lemmas, one needs to have some closure, but this is, not closed in any way. And so how do we deal with this? Well, it turns out, if something is not nice and you don't want to deal with it, well, let's just avoid it. So it turns out that one can build a lot of other intermediate models between R and R star. So this is the idea of the proof that I'll outline in whatever time I have left. The idea is to define intermediate models between R and R star. Use branch preservation lemmas to get the branch to be in those intermediate models. And then show that as a whole, they approximate the main model closely enough that you can actually define the branch in the main model. So any branch preservation lemma can be done without having to analyze this not nice quotient. So this in a nutshell. And so what are those intermediate models? So fix a name, a precree name, so an add name Q for a precree condition for an element in I. Okay. And we define with same underlying set, but a new order, and the order is, I'll call it less than R sub, Q dot, to be such that, again, we keep items 1 and 2, but in item 3, we don't take 1, we don't take this, but we take A prime Q dot restricted to alpha forces that R prime of alpha is stronger than R of alpha. So we keep some interaction between the coordinates, namely we keep the interaction from the Cohen part, but we remove the interaction from the precree part by just fixing this Q dot.
We also take the universe so that we give the conditions that
No, the underlying set is the same. So again, two conditions. So this is fixed. That's why it's fixed. The underlying set is the same. A prime, P prime, R prime is stronger than APR if this holds, and for every alpha in domain of R, A prime Q dot restricted to R forces this. So
also you require the P and P prime stronger than this Q.
well, yes, well, you can. You don't have to require it, but if you want to show that R Q dot projects to R, it will have to be R below. I mean, I'll write this down. But this can actually be defined ad hoc like that. Okay, and now, okay, so let's see. Now, by the way, for the rest of the time, I mean, we're just concerned about showing the tree property at the first successor because everything else has been done. Okay. So now, what is the picture, the models and the picture that we have? We have the following. So first, so as before, R star can be written as the product A times I and some forcing Q. Okay. Now, what about R sub Q dot? Well, R sub Q dot can be written as this interesting thing. A star, I mean, we need the A. There is no way to write it as a product where the second component is independent of A, because we do keep the interaction with the first coordinate, but here we have I dot and times another forcing, which I'm going to call, I guess, Q sub, that's not a nice notation, but anyways, Q sub Q dot. Where, so as before, in the R star case, now that this last component, this is mu closed. Now, in this intermediate model, this last component it's no longer mu closed because we do keep interaction of the first coordinate, but it is kappa closed because we've removed the interaction with the pre-creposet, which is not even countably closed. Namely, if you just look at this condition 3, it is kappa closed because we just have to worry about closing off those A primes, that's kappa closed. R of alpha is forced to be in a poset with good enough closure, and the pre-cre coordinate is fixed, so that doesn't change when you take a decreasing sequence. So this is kappa closed. Okay. And moreover, we do have that R star projects to RQ sub dot, and a projection is witnessed, for example, by the identity, which is order preserving, and its projection in the sense that for any condition in here, any condition in here can be extended with respect to this order to a condition that's also stronger than this, the usual diagram. So a generic for R star gives a generic for RQ dot. And unlike the quotient R star mod R, this quotient is nice because, I mean, you can mod it, both of them by add, and then you have the pre-cre part, it's kind of the same, you can mod out by it, and then you have one closed forcing over another. So that's a nice quotient, much more amenable to branch preservation lemmas than the R star mod R. Okay, and now also this projects to R, but with, as Moti mentioned, with one caveat. We have to take R below a condition whose pre-cre generic will contain Q dot. So below, say, 1 Q dot 1. So if you restrict yourself to all elements below this triple. Okay. And so the moral of the story is that R star mod R Q dot is nice. And we'll be using this quotient to do branch preservation lemmas. Right. So now,
P of U. What will be of U? Just according to the name of the tree?
Yeah, so the branch lemma that I need will actually look at, so for a given stem, it will look at all conditions with that stem. So for the proof, one needs more than just a branch preservation lemma for each one of these, but needs one for all of them simultaneously, but I'll get to it. Let me just say right now that this quotient is nice. So next, I want to say how these generics for these models will approximate R. Maybe this will partly answer Moti's question. So now, let G be R generic. Okay. 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 So let G be R generic. So let script A star I be at star, I dot generics induced by G. Okay. So far, so okay. Now, for every Q in the Prickly generic I, let GQ no, before that, let me say, let G star be R star mod G generic, and in a second I'll also draw a picture. R star mod G generic, and for every Q in I, let GQ be R Q generic induced by G star, and the picture is the following.
But wait a second. This always exists because we said that R star projects to RQ only.
No, R star always projects to RQ.
Oh, I see.
RQ projects to R below, but that's why we take for Q in the generic for the Prickly.
Okay.
So the picture is, maybe I should keep the order. Oh no, get rid of this. Okay. So the picture is, so here we have VG star. We have things VGQ for all Q, for every Q in this generic I. So there are, many models here like that. Okay. Because those Qs were taken from I, each of these models projects to VG. And some wrong pictures, I might as well say, VG projects to VA followed by I, which projects to V script A, where I didn't say, but script A is generic for add. Okay. And this quotient is the nice one. Why? Because so GQ, that's so G star, that's R star, which is A star I times Q. So in particular, this projects to V A, let me call this script Q, where script Q is generic for math BVQ. Okay. I take away the Prickly part, and this VQ projects to V A times, so not times, star, oh no, this is Q, script, so Q sub Q, I should have used P, I guess, maybe I should use P. Q sub P, where script Q sub P is generic for the appropriate defined poset taking the third coordinate with this order and working in VA. So, oh yeah, so it's the quotient for this, generic for this poset in line 2 of that board. Okay. So now, and this is, we kind of use the interaction between those two models to work with our branch lemmas. And the following observation, anyway, this is a nice lemma, maybe here. When I said that those models, the intermediate models approximate the main model, well, it turns out that actually G, the generic, is the union of G, P for P in I. Why? Well, so proof, I mean, it's a density argument, kind of playing around with the name. So given, so I mean, this direction certainly follows, because all those projections are witnessed by the identity. For the other direction, given, so fix some condition, some triple S in G, we want to show that S is in one of those GPs. Well, let's take the set D to be the set of all S prime, such that, and here, I mean, it's the same underlying set, but I want to specify R star mod G such that there exists P in I S prime is less than or equal with respect to R sub P of S. This is dense, but with respect to which order? With respect to the order R star mod G. And it's a nice exercise in names and orderings. And once you show that this is dense, okay, so intersects G star, and then, but by upwards closure, that, so if we take some S prime in D intersection G star, well, that S prime has to also be in GP, and by upwards closure, S is in GP. Okay, so I have, I guess, 5 minutes. Maybe I'll write down the statement of the splitting lemma that makes it all together and talk about it a little more in the beginning of tomorrow's section. Okay.
Let us just postpone
Okay.
again to the density argument. So this is dense with respect to R star over G. You take S prime now, which is in D intersected with.
I mean, it's kind of an exercise.
Yes, but your names, you know, there are so many generics. I'd like to understand this exercise. So D intersected with what?
Oh, okay. So you take some. So suppose you take some S star, then because both S star and S are in G, so this is R star mod G, they have a common extension. You have that. You take that common extension with respect to R. And this common extension, the second coordinate, the pre-cre coordinate of this common extension will be your P. I mean, it's a little bit more, one has to do a couple of extensions, but you use the fact that you're operating in R star mod G. So any condition in R star mod G will be compatible with S by a condition in G. And you take that pre-cre coordinate.
Okay, thanks.
Okay. So, I have my picture. Okay, so where's the picture? Okay, so now we're showing the tree property. So fix a tree in here. Okay. All right, now by Anti-Tice arguments and the indestructibility of the kappa n's and the fact that Q is close enough, one can get a branch in G star. So how do, maybe I'll just say something kind of more informally and then get more technical, or technical in a nice way, tomorrow. How does one pull those branches up to VG? Well, the idea is, well, suppose it's not. Let's look at all the values, all possible nodes that are forced to be in B, and show that you cannot end split forever. Because if B is truly a new branch, if B was not in G, then you have the situation where you have some node U, which is forced to be in the branch B by some nice quotient forcing, but then you can split it to incompatible nodes U1 and U2 such that both are forced to be in B. And this is how the splitting arguments usually work. So here, since we want to restrict ourselves to this quotient, this is a nice quotient, there are several things we need to do. First, instead of working with the tree itself, we want to work with a name. So this tree, T, one can define names in a way so that given the right generics projecting to each other, those names will have interpretation of the same object. And one can get, and this is why, although this is formally incorrect, for now I'll just put T dot for both of these. So there is a name for this tree in both of these models, and one can define those names so that their interpretation will be the same if you take projecting generics. Similarly, there is a name for this branch, D, in here. Now, this will be an I name. So, a pre-free name. Okay. And we're going to do splitting between, so for this quotient, but we're actually going to do, so this picture is just two splitting. We need splitting that has size kappa omega. So we actually need for each of these ui, where I is less than kappa omega. So similar with the same flavor as the Magidar-Shala paper, new splitting. And to get this new splitting, and also this will be splitting for something I thought, and I'll define it just tomorrow formally. But H splitting, that means any splitting between U and its nodes for VAQ mod VAQP, where P has stem H. So the branch lemma will fix a stem H and will consider all possible conditions of that stem H. And in order to get simultaneous kappa omega splitting like this, I rely on the precise statement of what was proven in Niemann's paper, which is how I ended last time's lecture, which was, so not only do we know that we have this branch B here, but we know that we have this unbounded set mu and of mu and pre-Cree conditions P alpha alpha in J such that P alpha meet P beta forces that, the nodes he defines are comparable, and each P alpha forces that, your sequence of nodes U alpha is in your branch B. And so using the fact that you have those things simultaneously is how one gets this splitting. And what else do I want to say now? Okay, so the branch lemma will be that you cannot have H splitting forever for any given stem H. So for any given stem H, let alpha H be where the H splitting stops. Take the supremum of all such alphas. The number of stems is less than mu, so the supremum is less than mu. Take a node above that supremum, and then whatever are the successors of this node will define your branch, because there's no more any splitting. And this lemma tells you that if there is an R star mod R splitting, that there has to be an H splitting somewhere. In a nutshell. Yeah. Okay. Sorry, I went over time again.
It looks like the question
better?
Here, and we meet again.